Hello and welcome to another video. In this video, we will see about the system with disturbance. So how can we control a system by using a proportional integral, proportional derivative and proportional integral derivative controllers when a system is affected by disturbance. We will see this example in all four different cases. Suppose we have the system 100 divided by 2s plus 1 and the disturbance model as 3 divided by 2s plus 1. The disturbance z of s is a step disturbance and the input u of s is 0. The output is y of s. First problem, we will see what happens when we use a proportional controller with the proportional value, the gain kr equal to 1. The input u of s is equal to 0. We can redraw the above diagram into this following way. Since the input u of s is 0, z of s will start from here. Z of s is multiplied with 3 by 2s plus 1, that is the disturbance transfer function. That is given to this summa. The summa is same as summa. And the output is taken as the out of the summa y of s. And a feedback is given here. Since the input u of s is 0, it is given directly. And this negative sign will have the effect here, minus 1. That is given again to 100 divided by 2s plus 1. That is given to the summa. So this is just a redrawing the above diagram. First, we will simplify this feedback loop. Since it is a positive feedback, we have g of s divided by 1 minus g of s h of s. Here g of s is 1, the forward loop, the gain is 1. And in the feedback loop, we have 100 divided by 2s plus 1 multiplied with minus 1. So after substituting, you will get the transfer function, the simplified block of this part to be 2s plus 1 divided by 2s plus 101. Now this block is in series with 3 by 2s plus 1. Hence, the total transfer function y of s divided by z of s will be the two blocks which are kept in series, multiplying the two blocks which are kept in series. That will be 3 divided by 2s plus 101. Suppose you are giving a steady step input to this disturbance input, z of s equal to 1 by s. Then what happens to the steady state value of the output? So limit of s tends to 0 by applying the final value theorem. After applying the final value theorem, we will get the value as 0.0297. So the final output will be approximately steady state value of the output y of s will be 0.0297. What does this mean? This means that the output which was initially at 0, due to the disturbance, it responds and finally settles at some value which is near to 0. It is not equal to 0. It is near to 0. 0.0297 is the final steady state value. Since we are using only a proportional controller, the proportional controller will have an offset. So this is the value of that offset. Now we will move on to the PI controller where we can eliminate this offset. So we will see how to derive the equation and how to check the steady state value so that the PI controller eliminates this offset and settles perfectly at the y of t steady state value at 0. So for the same system with the system transfer function, open loop transfer function as 100 divided by 2s plus 1 and the disturbance model as 3 divided by 2s plus 1. For a step input of the disturbance, what happens at the output when we are using a PI controller? Here we are taking the value of ki is equal to 2 and ti is equal to 0.5. What will be the steady state error for a step input for the disturbance? Similar to how we draw the reduced block diagram, equivalent block diagram for the previous problem, here we have the equivalent block diagram as like this, and we derive the reduced transfer function of this positive feedback loop as the PI controller's reduced form will be minus s plus 2 divided by 0.5s after cross multiplying, and that is kept in series with 100 divided by 2s plus 1. Hence this part, the feedback part will be, since both the blocks 100 divided by 2s plus 1 and minus s plus 5 divided by 0.5s. Both the blocks are kept in series. We just multiply them together. After multiplication, it will become minus 200 divided by s into s plus 2 divided by 2s plus 1. Now to reduce the positive feedback loop, we will have g of s divided by 1 minus g of s h of s. So that will be equal to s into 2s plus 1 divided by s into 2s plus 1 plus 200 into s plus 2. Both the blocks 3 divided by 2s plus 1 and s into 2s plus 1 divided by s into 2s plus 1 plus 200 s plus 2. Both the blocks are in series, so we just multiply them and cancel off the terms to get the entire transfer function between y of s and z of s as 3s divided by s into 2s plus 1 plus 200 into s plus 2. Now, by final value theorem, we have ESS is equal to limit s tends to 0, s into f of s. Unit step disturbance to the system. The steady state error will be 0 due to the presence of s in the numerator. Steady state error will be 0. So due to the PI controller presence, there will be some oscillations, but still the final value will be 0. So whenever you input a unit step disturbance to the system, the final output still be at 0 due to the presence of proportional integral control. The integral part makes the error 0. Now for the same system, if we use a proportional derivative controller and give a unit step as a disturbance, what will happen to the output? Here the KD value is 2 and TD value is 1. And after rearranging this block diagram, by reducing the positive feedback loop after the rearrangement, we get, this is the reduced form of the PD controller, minus 200 divided by 2s plus 1 into s plus 1. Sorry, this is the reduced form of the two blocks in series. So the feedback loop altogether will be minus 200 divided by 2s plus 1 into s plus 1. So for the positive feedback loop, the reduction is g of s by 1 minus g of s h of s. Here g of s, the forward path gain is 1 and the feedback path gain is minus 200 divided by 2s plus 1 into s plus 1. So substituting that, we get the reduced transfer function of the positive feedback loop as 2s plus 1 divided by 202s plus 201. Now that is in series, that this block is in series with 3 divided by 2s plus 1. Hence we just multiply them to get the entire transfer function between y of s and z of s. So after multiplication, the two blocks in series 3 divided by 2s plus 1 and 2s plus 1 divided by 202s plus 201, we get 3 divided by 202s plus 201. So this is the entire transfer function between the output and the input. Sorry, output and the disturbance input. So for the steady state error ESS, we get limit s by applying final value theorem. We get limit s tends to 0 s into f of s. That is equal to limit s tends to 0 s into 1 by s, because 1 by s is the step input that we are giving to the disturbance here. Into the transfer function of the block 3 divided by 202s plus 201, which we have derived here. That will be, after substituting, that will be approximately equal to 3 divided by 201. That is approximately equal to 0.0149. So that means for a unit step disturbance that we are giving for Z of S, the output will look something like this. So the output will fluctuate, but will settle at some value 0.0149. So there is no integral part here, so there will be still an error. So the error is, the steady state error is 0.0149. It will not perfectly settle at 0. There will be some steady state error here, that is 0.0149. Now we will move on to the proportional integral derivative controller. So now what happens when, for the same system, the same disturbance model for step input disturbance, what happens for if we use a proportional integral and derivative controller? So the general form of proportional integral derivative controller is kr into 1 plus tds plus 1 by tis. So this is the integral part and this is the derivative part with kr as 2, ti as 0.5 and TD as 0.5. We will see what happens to the output. So now this is a modified diagram. Here Z of S is the disturbance. Here we are giving a step disturbance. 3 by 2s plus 1 is the disturbance model. Now this is the positive feedback loop. Within the loop we have in the feedback minus 100 divided by 2s plus 1, 2 into 1 plus 0.5s plus 1 by 0.5s. So these two are in series, we can multiply them. After multiplication, you get minus 100 divided by s square plus 2s plus 4 divided by 2s plus 1. Now this is in the feedback loop. Now to reduce the positive feedback entire block, whichever is in the dotted line, we use the formula g of s divided by 1 minus g of s h of s. After substituting and rearranging g of s by 1 minus g of s h of s, we get s into 2s plus 1 divided by 102 s square plus 201 s plus 400. This block is in series with 3 divided by 2s plus 1. Hence we multiply them together to get the transfer function y of s divided by z of s is equal to 3 divided by 2s plus 1 into s into 2s plus 1 divided by 102 s square plus 201 s plus 400. So after cancelling off the terms, we get 3s divided by 102 s square plus 201 s plus 400. To get the steady state error for a unit step disturbance 1 by s, we get limit of, by applying the final value theorem, we get limit s tends to 0, s into 1 by s into 3s divided by 102 s square plus 201 s plus 400 is equal to, after cancelling and applying s tends to 0, since in the numerator we have s equal s term, we get the steady state error as 0. So whenever we apply a proportional integral derivative controller, the steady state error will be 0. So these are the 4 different cases where we applied the proportional integral, proportional derivative and proportional integral derivative for a system that is affected by the disturbance. We have seen the proportional integral and the proportional integral derivative controller perfectly eliminates the steady state error ESS to 0 due to the integral component. But proportional and proportional derivative controllers still have some error, steady state error in them. So we will see few more examples in the next videos. Thank you.